All right, hello two triggers, welcome back. We are in week 2 of remote learning. This week we're going to be learning about a new type of angle measure that is called a radian. Radians are another way to measure angles. They are mine and Mr. Schulten's favorite way to measure angles more so than degrees. And they have a lot to do with the construction of circles in general, so they tie into the unit circle really, really well. In order to start this, we're going to actually go do a video animation to watch an animation. I'm going to try to talk through it. I may have to pause it if it moves faster than I can speak, which is rare because I talk fast, but let's see. Okay, so here's our animation. So let me play this. So if we start from a point, we measure out some distance, and then we rotate around that point. We've created a circle, and that length that we've made was a radius. Now if we take that radius, we stretch it up and curve it over to be an arc length of a circle. The interior angle that we make when we have an exact radius length along the outside arc of our circle, the interior angle that we have made is called 1 radian. So that green angle measure inside is called 1 radian. So let's write that down. Let's go back to the definition. Based on this picture that's right here, the thing that we can see that's right here along the outside, this is the radius in distance, in the same way that this is also the radius in distance, and so is this one, the radius. But the angle measure that's here inside, that one is a radian. And what a radian is in definition form is exactly what we just showed you. It's the angle formed at the center of a circle when the arc length is exactly 1 radian. Oops, sorry, I just said that backwards. Sorry. A radian is the interior angle in the center of the circle when the arc length is exactly 1 radius. Those words are really, really similar, and I'm going to say them backwards. Apologies. So, with that in mind, my next question is, how many degrees do we know exist in a half circle? Well, that's a fact that we probably already know. 180 degrees exists in a half circle. My next question, though, is how many radians exist in the half circle? So I'm going to go back to my simulation and allow the simulation to answer that question for me. So we can see 1 radian. It exists solely in the first quadrant, regardless of the size of the circle that we use. Regardless of how big or small that radius is, that will always be the case because it is proportional to the circle. So 1 radian exists solely in quadrant 1 in this case. If we keep going, we can make a copy. And there's a 2nd radian. It's now spilled over into the second quadrant. We're able to get 3 and just a little bit more radii or radians in this half circle. We got 3 full radiuses or radii around the outside, plus this little bit of extra. That little bit of extra has been calculated over and over and over again and approximated and tried to find the exact value, and mathematicians found out that that extra little bit was 0.14159, continue on with that crazy decimal that I don't know. But what it actually turned out to be is 3 plus that little extra bit meant that there was exactly pi of those radii that could fit along the outside, meaning that they were pi radians that fit along the inside. So in half a circle, there are pi radians. Pi radians. 3 and a little bit more. And the reason this is really helpful is because radians are a really interesting measure to be able to see in the circle, knowing that if we have half a circle is pi, a full circle, well, that's 2 half circles, is 2 pi radians. I've probably been honing it into your brains a bunch of times that you need to write that degree symbol when you're writing down units previously. That is because radians get to be our unitless measure. So if we write down an angle measure and don't put any units, the assumption that we can make is that it is in fact in radians, which is a little bit strange. But that's an assumption that we weirdly can actually make. So when we're writing in degrees, we have to be super, super careful to annotate and actually use that degree symbol. Okay, the next thing that we want to think about is how do those degrees relate to radians? So let's say in, 90 degrees. There are multiple ways to think about how we can convert or think about going back and forth between degrees and radians. One that feels very computation heavy and one that feels a little bit more logic based. So we're going to talk through both. So let's think about it. If we had our unit circle like this, we know that half a circle right here, that's pi radians. And we know that 90 degrees splits that up directly in half. So what that really means is that right here at 90 degrees, we have half of that pi. Half a pi radian gives us pi radians by the time we are halfway around the circle. By just simply splitting up our circle into 4 equal pieces. We could also think about this as here's piece 1, here's piece 2, here's piece 3, and here's piece 4. We know the full circle is 2 pi, and we're splitting up that full circle into 4 equal pieces. So our 90 degrees is then equivalent to the full circle divided up into 4 equal pieces, or pi over 2, pi halves, as we would say. Now that way is very, very rooted in logic, either thinking about, well, it's half of the half circle, or it's a quarter of a full circle, which is a wonderful way to think about it, and actually to me seems more natural and logical. But we can also think about this as some type of conversion. Now for converting things, I want to go from 90 degrees and eventually I want to be in blank radians. And in chemistry classes and possibly in previous math classes and maybe even earlier this year, whenever we're converting units, what we're always doing is trying to find that magic 1 that we will multiply by. So let's say we took our 90 degrees, I'm going to put it over 1, and then we want to think about what is that magic gigantic 1 that we would want to multiply by so that we end up with something that is in radians. The conversions that we know, there's 2 of them that we actually know that could be possibilities to go here. We know that the full circle, that full 360 degrees, is equal to 2 pi. And we also know that the half circle, 180, is equal to pi. Either one of those 2 ratios can be helpful to us to be this big gigantic 1. So I'm going to use the second one just because it's a more reduced expression. In this case, we know that pi is equal, We know that pi is equal to 180 degrees. We want to be in terms of radian and cancel out the units that are actually in degrees. So we're going to use 180 degrees down below and pi on top. And because those 2 things are equivalent, it's like throwing a giant 1 into this equation. And now I know it's my least favorite word in the world to use as far as canceling out, but the degrees and the degrees, when we divide by degrees, they disappear from one another. And then I can be left with pi divided by, 90 pi divided by 180. And then we can do a whole lot of division or reducing, or however you want to think about it, and we end up with pi over 2 radians. Pi over 2 radians. So we can think about it in the unit conversion way. We can also think about it as a type of logic. So similarly, we can go the other direction. If we have 2/3 pi radians and we want to put that back in degrees, now my favorite way to do this is to try to visualize what 2/3 pi radians would be, or 2 pi thirds. 2/3 pi radians. So we know pi radians would be the entire 180 degrees, this top half of the circle. And we know we have a little bit less than that. We have 2/3 of that. So let's see if I can split this up into 3 equal-ish pieces. That's not super equal, but it'll do. We'll pretend that this is perfect thirds that we've got going on here. Oops, I'm making more of a mess than it's worth. But if I've got 3 equal pieces of this thing, and I know that I had 2 of them, well, let's think about what's going on here. In radians, we know that we've got 2/3, meaning we've got this one and this one. In degrees, things that we know is that, well, that same half circle is 180 degrees. Split up into 3 equal pieces. Each of those pieces is 60 degrees. So that's 60 degrees, that's 60 degrees, and this is another 60 degrees. So if we only have 2 of those 3 pieces, what that really means is converting this into degrees. 2 pi thirds is equal to 60 plus 60 degrees, those two little pieces, or 120 degrees. Similarly, if you would rather think about the unit conversion type solution, we can take our 2 pi thirds that's in radians. We're going to again use that gigantic one to turn it into degrees, and this time we know that pi radians is equal to 180 degrees. Pi divided by pi cancel each other out because they turn into 1, and then from here I've got 2 times 180 divided by 3. Well, that's 360 divided by 3, or 120 degrees. Like that. Either way to convert between our radians and degrees. Now, at this moment, how do I keep zooming on here? I want to stop doing that. I would suggest that you pause the video and try to think about these special triangles. What about 30 degrees? What about 60 degrees? What about 45 degrees? What do those look like in radians? In super Dora the Explorer fashion, you're right. 30 degrees, that is pi over 6. 60 degrees, that is pi over 3. 45 degrees, you're right, that is pi over 4. And the reason that it's important to think about these in terms of radians as well is because now I could ask you the question like, what is sine of pi over 3? And now that's a problem that you can actually solve. Or I could ask, sine of theta is equal to root 2 over 2. What is theta in radians? And again, now this is a question that you could answer. If you want, in this moment, pause the video, try those two things. Dora says, you're right. Sine of theta equals root 2 over 2 in radians is pi over 4. Or sine of pi over 3, you're right. It's root 3 over 2. Absolutely. So this wonderful half sheet that or not half sheet, but a graphic organizer sheet that we had from before might be helpful at this moment. It may be beneficial for you to add in the radian measures on these special right triangles as well, because we're going to kind of move into a land of radians for a bit and do some solving in radians. So I suggest that you do that. I'm not mandating anything though. Oh, no, can I just skip to the next one? There we go. All right, and now on to the last little bit, your entrance ticket. Here's your entrance ticket. First, I want you to out loud rephrase and explain what a radian is. Then you're going to convert 5 pi sixths from radians into degrees. So I would like you to try to do this without looking at your notes, if at all possible. Write it out on a piece of paper and then submit it to our survey on Google Classroom. Good luck with all of this. Second block wants me to remind you all, don't forget to like and subscribe. I don't know what the last part means, but something about ring that bell. So do all of those things now, and I'll see you guys in class on Tuesday. Bye.